Good afternoon, everyone. My name is Cesar Alonso Ruiz Alexander. I am a PhD student at Universidad Iberoamericana in Mexico City, and today I'm going to be giving a little talk on a project that I have been developing the last couple of months, and it's called A New Way to Analyze Iterative Systems Through Topology. Okay, so in order to properly contextualize the project itself, we need to go over what iterative systems are in the first place. So these are particularly simple to define. You start off with a space x and a function f that's defined from the space to itself, and you define the system as the collection of all possible sequences defined iteratively as follows, where the next point in the sequence is going to be the result of applying the function f to the last point in the sequence, and of course these sequences span over all possible starting points in x. Okay, so a very simple system to define. It's very straightforward. So of course one could ask ourselves what types of questions are of interest regarding these systems. What types of things can we probably look forward to research or to ask ourselves about, and of which there are a couple. The first one of which is the ability to categorize points based on their long-term behavior. This is, of course, if the point is, for example, periodic, which means that if you start at a given point and you apply the function enough times, you will come back to the starting point, to the point you started with. Pre-periodic, which are points that, given enough iterations, eventually settle into a periodic point, or some other behavior that is proper to the space itself. The point can, for example, blow up to infinity. They can converge to a single other point in the space. They could probably loop around in cycles without really, being periodic themselves. There are a lot of different behaviors that the points can take, and these are, generally speaking, dependent on the space itself and the function. Another thing that might interest us is a way to categorize these systems in a way that does not entail an explicit computation of every point's behavior. Of course, not only because this kind of defeats the purpose of the whole reason why we're studying them, but also because of the fact that it's infeasible for spaces that are infinite in nature to compute every single point. Of course, it is very expedient and obvious to establish a point's periodicity by merely applying the function to itself enough times until you get the same result, but that just kind of defeats the whole purpose of trying to categorize these types of points by doing something different than just applying the definition, right? A criterion akin to Bannach's fixed point theorem would probably be ideal for those. This is probably the most well-known result with these types of spaces, and it establishes the behavior of every single point in a complete metric space, provided the function itself is a contraction. And again, this theorem, this very strong theorem, essentially delegates the entire behavior of the space to topological properties, which is something that we would probably find ideal in order to truly motivate our research. And of course, the last of which is probably the most oniric of all of them, and it's a way to apply these to unsolved problems looming over the discipline. Of course, there are a lot of unsolved problems, and we would probably like to contribute to the solution of some of them. And despite the simplicity of not only the definition of the system itself, but also of the questions in nature, most of these types of questions lie out of reach, or at least generally speaking, each result being contingent on the structure of the set X or the function itself F, as mentioned before. Sometimes you need the function to satisfy some very stringent set of requirements to properly establish something. And one can even come to believe that maybe every single possible result in the matter necessitates some sort of extraneous aid to establish, right? And if this were the case, then what can we do about spaces with little to no inherent structure? Again, these spaces that things have been established with have been, metric spaces, the real numbers, finite spaces that we are probably consider very well understood, but of course there's a lot of different other spaces that don't have the amicability that these have. An example of these types of spaces is the natural numbers, and perhaps the most natural, pun intended a little bit, of all possible spaces. And it is home to a wide array of conjectures, most of them unsolved as of this moment, that ask essentially the same things. Perhaps the most famous example of which is the Collatz conjecture, also known as the 3n+1 problem, which states that the iterative system defined by a specific function, which of course has 3n+1 in its definition somewhere. That's the reason why the problem is called the 3n+1 problem. But it not only specifies that every single point is pre-periodic or periodic, but also further strengthens this hypothesis and asserts that every single point ends in the cycle, in the pattern 4, 2, 1. And then it repeats itself ad infinitum. This is, of course, a very strong conjecture, and it's still, as of the recording of this video, very much so unsolved. From what we can gather, there has been some recent developments by Turnstile, who attempted to solve the conjecture using some vastly different methods to the ones that we will be using. We will be trying to establish in this talk. From what we can understand, this conjecture is very much so at this very moment open. A couple of examples that ask the same question are the Catalan-Dixon conjecture and the Jacobus conjecture, which both affirm that given the respective systems, no point blows up to infinity. Of course, these are obviously unsolved. Catalan-Dixon conjecture is actually intricately related to perfect numbers. So this is, again, a number theoretic type of connection that we're establishing here. But of course, not every single conjecture of this sort is unsolved. We also have an example of a solved problem, which is Goodstein's theorem, which states that every single possible sequence terminates, and this problem was actually solved, and it was solved in a very non-trivial manner, since it used the theory of ordinals, which is very much so much more complicated than what was used to define the conjecture itself. So this is just an example that can help you elucidate the fact that these questions are very much so not as trivial as they appear to be at first glance. Okay, so this is where we hope our topology can aid in the solution of these problems by establishing a connection between the system's long-term behavior and the space's topological properties, right? We call our topology the dynamic topology induced by f in order to denote the fact that it is in fact beholden to the function f. And our research currently focuses completely on the natural numbers, but this very general definition, can be applied to many other spaces, and there's actually a way to further generalize it in a way that we will go over once we go over the definition. So the only prerequisite to establishing the definition is to introduce sets that we call stable. These are sets that satisfy the following condition: that the image of the set under F will be the same as the set itself, A. This, of course, you can call these types of sets invariant under F. We prefer the term stable. It's again just a matter of taste, I guess. And given those sets, we define the following non-total sets as closed. So we start with a set C, and we define the set as closed if given enough iterations applying enough iterations of the image on the set C, it will be contained in some stable and finite set. Now, we should remark the fact that the condition of being finite can actually be swapped for any condition that is preserved under finitely many unions and arbitrarily many intersections. The reason why we settled for finiteness in the context of natural numbers because it has a very straightforward relationship with periodicity, right? Okay, so that's again just the technicality. So again, the question that you might have is, what types of properties do these spaces enjoy that are relevant to this discussion, right? And over the natural numbers, we have established quite a couple. We will go over some of them. The first one of which states that the space is T1 if and only if every single point in the system is pre-periodic, right? Well, remember that a space is T1 if and only if every singleton is in fact closed. Another way of saying this is a point is closed if and only if it is in fact pre-periodic or periodic in the original system. Another interesting condition is that the space is path connected if and only if there is at least one point that blows up to infinity. Of course, if there's a point that blows up to infinity, there has to be infinitely many. It's actually the case that the space is actually totally path disconnected if there is no such point, which is interesting for reasons that we will establish later. The dynamic topology induced by a function f is equal to discrete topology if and only if the function's image becomes finite after finitely many iterations. And this is actually very interesting since, again, the topologies that do not satisfy the aforementioned condition, their spaces are actually irreducible. So again, a lot of properties that kind of, mount into having this reputation for these topologies being the topologies of extremes. That's a very affectionate way that we have come to know them. Another example of which is that every set in this topology is either closed or dense. And that not only that, but the subsets of closed sets are also closed. And finally, that continuous functions, or at least a set of functions that we have established their continuity under this topology, are intricately related with the centralizer of the function f. This is interesting since it creates a bridge between the algebraic, which is a centralizer, and the topological, which is continuity. So again, these are very interesting, and one can find a very clear path of connections, right? So these properties, what they do is that they constitute bridges between the long-term behavior of the system and the topological properties of the space. There's, of course, probably a lot more that we haven't yet established, but they're interesting to think about. So in general, these topologies are very, very strange, right? So this is something that should be kind of like a caution to the reader, to the spectator, since these are in particular very strange. We finally have lastly have some examples of what the dynamic topology of some well-known functions are. So constant functions, we get the discrete topology due to the aforementioned condition. The identity function actually begets a co-finite topology, and if we have x to the n with n bigger or equal to 2, we get the topology of the excluded point with excluded point 1. This topology in which a set is open if and only if 1 is not an element of the set, which is a very interesting topology to get so naturally. And there are also work examples of topologies that are strictly larger than the co-finite topology, in the sense that there are some infinite sets that are closed. Matter of fact, a topology contains the co-finite topology if and only if every single point is pre-periodic or periodic, which kind of acts as a natural barrier between these types of systems, or at least topologically speaking. Okay, so what can we expect from future research? We would like to embark, for example, there are 3 avenues that we have identified. First one is to embark into the algebraic topology of these spaces, perhaps a fundamental group or some type of homology. We could also focus on specific subsets, a subset of all possible functions subclass, or to gauge more specific properties proper to them, an example of which would be multiplicative functions like algebraic functions, and functions of interest to number theory would probably be interesting. We could also expand horizons, analyze the dynamic topology of functions in other spaces. An example would be in C. By altering the definition of dynamic topology, should it be necessary, we could, for example, exchange finiteness with boundedness. That probably would be interesting in the case of the complex numbers. Well, thank you very much for listening. I hope you had a very interesting time listening to this expository talk about this project that is very much so still in its infancy. We hope you found it interesting, and if you have any questions, please just let us know. Thank you very much for everything again, and I hope you have a really good time.